Mm. Very small part remaining. So after finishing this, we will go to the op-amps, operational amplifiers.
Okay, next we will move to the second order filters. So if first we consider second order low pass filter, because if it is second order, it contain R, L, C all, right? So this figure, this circuit gives second order low pass filter, RLC, because output is taken across the capacitor. Then that will become a second order low pass filter, right? If you remember the first order low pass filter, we had only R and C, output was taken by C. But when it comes to second order, in addition to the resistance, there is an inductor in series with that, right? So for this filter also, resonance frequency is becoming same, 1/2 square root of LC, and quality factor is equal to L omega over R, right? That is 2πf0 L over R. And also you can write in terms of capacitor like this, 1/2πf0 CR, same, not changing, right? So, and in this graph, you can see transfer function, H variation in the Bode plot. That is frequency in the logarithmic scale and H in the decibel scale. And this is giving the Bode plot of the transfer function for different quality values, right? What you can see. This is the transfer function for the first order filter. This black curve gives for the first order filter. Blue curves gives for the second order filter for different Q values. Then which one is best in the second order filter? Because you know that if we want to obtain in a filter, what we want to obtain is that H value should be approximately constant in the throughout the band what we are interested in, because this is a low pass filter and this is the F0, so therefore the lower frequencies than this F0, right, it should have some approximate value. Therefore if you compare these different Q values, you can see when Q equal 1, this curve, it has some approximate value, no, up to F0. Therefore, when compare different Q values, Q equal 1 is the best, right? When we design a second order low pass filter, Q equal 1 is the best to obtain the more better results, right? This is second order low pass filter. Is that okay? Next, we will see how second order high pass filter. What is the difference? Now output is taken through the inductor, right? In the low pass filter, output was taken across the capacitor, inductor was here, but in the high pass filter, output is taken across the inductor and capacitor here. Now that becoming a high pass filter, right? So here it is given the Bode plot of this filter. What you can see again, higher frequencies, F0 is here, these are the higher frequencies, so you can see approximately Q equal 1 is again best, no, for the high frequencies. Therefore normally when design second order high pass filter, QS is maintained at 1, right? Next, second order band pass filter. That is, we have to pass a band. Band is different between two frequencies, F2 and F1. You know that these relations B equal F naught over QS, and F2 and F1 we can obtain by this. We already discussed. So band pass filter we can obtain by this. That is, we get the output across the resistor. Then it become a band pass filter, right? So Bode plot of the band pass filter is given here. Then depending on the pass, the band, what we have to pass, we can choose the best quality factor value, right? Normally it is passing a very small band. And band reject filter. Band reject filter is some frequencies are rejecting, but you can see here in this figure. At this F naught, it is totally going to infinity, minus infinity, totally rejecting. This is for different Q values. And so we can obtain band rejector in this way. Output is taken across both inductor and capacitor. Then it will become a band reject filter, right? So in the theory, transfer function should be 0 in this F naught, because it should not pass anything, right? We have to reject the band. Therefore, if we convert it into decibels, that should be minus infinity. Normal zero value should be minus infinity. Therefore, you can see it is going to very larger minus values, right? But we can't obtain totally minus infinity because if we get these inductors, that also has some series component is embedded in that inductor. Therefore, we can't totally get the minus infinity value, but we can obtain very large HF negative values by properly selecting L and C, right? These are band reject filters, second order band reject filters. Okay, so those are the main second order type filters. Now, I think it is clear that second order filters have all components R, L, and C. So depending on where we obtain the output, we can obtain different filters. That is, if we take the output across the capacitor, we can obtain low pass filter. If we obtain the output across the inductor, we can obtain high pass filter. If we obtain output across the resistor, it will become a band pass filter. If we take the output across L and C, that will become a band reject filter, right? Okay, now see this example. Suppose that we want a filter that passes components between F1 45 kilohertz and F2 55 kilohertz. Higher and lower frequencies are to be rejected. Design a circuit using 1 millihenry inductance. What is that filter? Frequency F1 and F2 given, 45 and 55, we have to pass. Therefore, that is a band pass filter, right? That is the band we have to pass between 45 and 55. Higher and lower components we have to reject. So, you know, we can obtain band pass filter if we get the output through the resistor. So you can calculate what are the values. Because L value is given, you have to calculate what is the C and what is the R. Right? So therefore, if we start from here, B is given bandwidth, difference between two frequencies, 10 kilohertz. Right? Then you can obtain what is the larger frequency. Larger frequency F2, you can write as resonance frequency plus B over 2. Then F naught should equal to F2 minus B over 2. So F2 is 55, B over 2 is 10 over 25. Therefore, F naught becomes 50 kilohertz. Right? Now you can get QS because from this relationship. QS become F naught over B 5. Right? Now again, you know that you can write QS by this way, L omega naught over R. Now you know L, U naught omega naught QS. Therefore, you can get what is R from this one. R is equal to this value, and by calculating, you will obtain what is R. Right? Similarly, QS we can write using the capacitor in this way, and you can get what is C. You will end up with 10.1 nanofarad. Then you can draw the circuit: inductor 1 millihenry, capacitor 10.1. This should be nanofarad, right? Nanofarad, and R should be 62.8 ohm. This is the filter, band pass filter we have to design for this given application, right? Okay, because you don't need 1 hour for eating, right? You are at home. Right, we will go to the parallel resonance. Right, here, because we have already discussed all the theories, and so therefore we can quickly go through this one. So because now you know the series resonance. Series resonance we obtain by a series connection of R and RCL. In the parallel resonance, the circuit configuration is like that. RCL are connected parallelly with the source, and also output is taken like this, right? So then if you consider this circuit, this is current source is given, different currents are passing through different parallel branches. If you get the total impedance of this circuit, right, that would become this one, right? Because normally you know that 1 over ZB is equal 1 over R plus 1 over XC plus 1 over XL. So if you write that equation and little bit adjusted, you will end up with this equation, ZP, right? But normally when we talk about the parallel circuits, you know it is easier to deal with the admittance than the impedance. Therefore, if we obtain admittance from this impedance, that will become this component, right? Here. Now you know that for the parallel resonance, voltage should become maximum or admittance should become minimum, right? So therefore it is easier to deal with admittance, and therefore we consider the condition YP should become minimum, right? So therefore what happened, and this is given the phase angle of the admittance, right? So if you see this admittance, what you can see, this will become in the minimum value if this term goes to 0, right? This is similar to the series resonance. That is why I am going quickly. This term should go to 0, then this will become a minimum value. This is going to 0 when omega C equal 1 over omega L, right? 1 over omega L. Then you will end up with the same condition as the series resonant frequency, right? Resonant frequency of the parallel resonance is same as the series resonant frequency, right? No any difference. And in addition to that, you know that we can obtain resonance at unity power factor, right? So therefore, that also you can consider. But when we go to some practical electrical circuits that may contain series parts, parallel parts, right? Then we can consider all the resonance things. That is, that should contain series resonance sections, parallel resonance sections. Then you have to consider all the possibilities. That is, current become maximum, voltage become minimum, like that, right? But normally, you know, not the current become maximum, we consider impedance become minimum. Similarly, here we consider instead of voltage, admittance become minimum. So all of these conditions we can take into effect when we go into the practical circuits, right? Unity power factor situation. And in addition to that, if we talk about the quality factor we can write as R over omega L, right? Or we can similarly write it as this way. This is 1 over or the reciprocal of the quality factor as the series resonance circuit. I think if you remember, I told you at the when we discuss about the quality factor, when we go to the parallel circuit, that will become the 1 over value. That is why we gave a common definition for the quality factor, considering the energy storage and energy dissipation, right? That you can see here. And bandwidth you can obtain by this equation, F naught over QP. I think in your lecture notes there should be this part is remaining. I think it has some mistake. Remove that. Bandwidth is related by that. So F naught over QP. That is, if we get F naught over QP is equal 1 over 2 phi CR. That is equal to bandwidth, right? Okay. Quickly go through some examples and stop. So this is, see this figure. But you can see here, there is a series part as well as parallel part, right? Find the types of resonance. That means you have to find all the possible types, right? And resonance frequencies. What can be happen here? If we get, if you consider this circuit, total impedance become R plus J omega L1 plus total impedance of this parallel combination. Parallel impedance you can obtain by J omega L2 into 1 over J omega C divided by addition J omega L2 plus 1 over J omega C. If you add that total impedance of this parallel path, parallel section with J omega L1 and R, you can obtain the total impedance. That you will get like this. Now you have to consider all the possible resonance conditions, right? One is that power factor becoming unity, right? That means equivalent impedance should become purely real, no any imaginary part, right? So that means this imaginary section should goes to 0. It is written here, right? J omega L1 and this part should goes to 0. If you solve that one, this is just the mathematically, it has been simplified and solved. You will get this equation. Omega square is equal to L1 plus L2 over L1 L2C, right? But you know that equivalent impedance, because if you see this figure, L1 and L2 are parallelly connected, no? Because this is series with resistor R1, but when it comes to this, it is parallel connected. Therefore, equivalent impedance is L1 parallel L2, right? Therefore, here it is something like that. Therefore, equivalent impedance we can obtain by L1 L2 over L1 plus L2. Here you can see that one as 1 over L equivalent. Therefore, it has been replaced by 1 over L equivalent into this C, right? Then unity power factor resonance becoming 1 over L equivalent C, sorry, square root of L equivalent C. This is one condition that can happen the resonance, right? That is considering the unity power factor. In addition to that, there is another condition, impedance of the circuit become minimum. Again, what happened? Impedance is this one. Impedance minimum being again this imaginary part goes to 0. Therefore, same condition. Right? Therefore, you don't need, no need to consider again. That is similar as the earlier part. And another condition that resonance can happen is impedance of the circuit is a maximum. Right? So that is this terms becoming maximum. So so we said have a maximum value if this component goes to 0. What happens if this is 0? This term become infinity. Then Z is maximum, right? Z is becoming infinity when this term goes to 0. Therefore, that component is to 0 is another condition that we can see the impedance, resonance, right? For this condition, we can obtain omega is equal to 1 over L2C. If you solve this, you will end up with this. Right? Now you obtain 2. This is 1 for the resonance. This is 1 over L2C, another condition. Right? That is the possible conditions for this situation. Right? I think now it is clear. When you get when you have a circuit and if it has both series and parallel combinations, you have to consider all the possible resonance situations. Power factor unity, impedance minimum, impedance maximum, all the conditions you have to consider. Right? And the final example. This is a configuration. Here what happened? Here L and R parallel with C. No? Find the unity power factor, resonance frequency. These values are given. Determine the parallel resonance frequency if R, L, C are given. First, what you have to get? You have to get the equivalent impedance. Right? L and R parallel with C. Therefore, equivalent impedance become R plus j omega L parallel with 1 over j omega C. Therefore, multiply product is divided by addition. Right? Those are simple things and I am not going to explain. Right? So, you will obtain the equivalent impedance. Then, if you modify this or simplify this one, you will obtain this expression. Right? Now what happened? Now you have to consider the possible conditions for the resonance. Right? Equivalent impedance should be purely real. Right? There is unity power factor condition and the impedance should become maximum or minimum. All conditions you have to consider. So therefore, if you get this impedance and solve, right, it has all in some specific way. That is because you can see here we have a plus part, and if you multiply top and bottom, that is denominator and numerator, by this component, that is 1 minus omega square LC minus j omega CR, you will get this one. Right? And when you simplify those, you will end up with this expression. And finally, what you have to say, this j component should goes to 0. Right? When we want to get the minimum impedance, this j component should goes to 0. Therefore, you can obtain that one, and you can obtain one of the condition for the resonance like this. Right? And also you can consider another condition, unity power factor. Right? Unity power factor also, you know that the admittance, that is j components, must go to 0 because V and I are in phase. Then similar, right? Similar to top one. Therefore, again this one, right? So, and then you know these values. L, R, C values are given. If you substitute those values, you will get the resonance condition for the unity power factor resonance. Right? Unity power factor resonance, you will get frequency as 729.3. Sorry, earlier because of this quick explanation, I get some mistake. Here we consider unity power factor resonance, right? Not the minimum impedance. To obtain unity power factor, this imaginary part must go to 0 because voltage and current should be in phase. That is why we will equal this imaginary part into 0 and obtain this condition. Therefore, this is only here we considering unity power factor resonance, right? Frequency becoming 729.3. In addition to that, you can consider the magnitude of the impedance. So this is the equation for impedance. So if you get the magnitude, you will get this value, right? Later you can check, because if you get here r square plus omega L square over this square plus this part square, right? R square plus omega L square and the denominator part, right? When you want to get maximum value of z square must be maximum to obtain that, because here it is difficult to do by the physical, that is just by seeing the equation, it is difficult to guess. Therefore, you have to use the normal procedure, obtain the derivative of the z square and equal it into 0, and you can solve and you can obtain what is omega. You will end up with this frequency. Therefore, this is the resonance frequency for the magnitude of impedance becoming maximum, and this is the resonance condition for the unity power factor. Therefore, we can identify two components of the resonance for this circuit. Okay, I went a bit fast, but
Right, so that's only on this resonance section. If you have any questions, please send me. There is one question. Why do we get the peak value for phasor representation? No, normally for the phasor representation, we use RMS values. I don't know why ask this question here, but for the phasor representation, we use the RMS values normally. No questions? So shall I move to the other section? Because in the second section, under dependent sources, we have to discuss about operational amplifiers. That part is remaining. That's only under the theory part we have to discuss, and the rest of the lectures will be done by Professor Vikramaraj. So you don't have questions, we can move to the op-amp. Operational amplifier.
Recording in progress.
So what is operational amplifier? I think some of you have worked with op-amps, because in electronic circuits, this is a very versatile component used in the circuits, right? So it can do various functions for addition, subtraction, multiplication, division, amplification, integration, differentiation. Likewise, various functions we can play with, that is with the signal, right? We can play with the signals using the op-amp. So this is the active element, active circuit element, and the dependent source, because this is voltage controlled voltage source. This is the dependent source. So if right. So if we get normally the how we represent op-amp, you can see here. Right, this is the way how we represent operational amplifier. Normally what it do is the amplification of the signals, but in addition to that, these functions also possible, like addition, subtraction, those things are also possible. So what are the terminals or the things you can see here? Here you can see negative terminal, positive terminal. Those are input. This is what we call inverting input. Negative terminal we call inverting input, and the positive terminal called non-inverting input. And also you can see here supply. Normally DC supply. positive side and negative side. And this is a reference, right? Ground or the reference voltage. And here we will get the output. This is the way of an operational amplifier. So therefore, you can see there are two input terminals, inverting input terminal and non-inverting input terminal. So if we further see the inside of a op-amp or an equivalent circuit, it is like this is inverting terminal, inverting input, this is non-inverting input, and it is connected with the resistance. That is what we call input resistance. And then there is the because this is amplifier. There is the amplification. A is the gain, right? Or the amplification factor or gain, what we call gain. So times VD, that is given as the output to a resistor, output resistor. So therefore you can see this output depend on VD. That is why it is what we call voltage controlled voltage device. So normally this, if we get values, this input resistance is very large. Input resistance is very large and output resistance is very small. Then only we can get some amplification signal as the output, right? In addition to that, if we get this amplification factor or the gain, it ranges between, sometimes it is around 10 to the power 5, or sometimes it goes up to several millions, 10 to the power 6. That is the gain of amplifier. And here the supply is not shown. That is just for the simplification. But normally the supply voltage, DC voltage for op-amp range between 5 to 18 volts, right? So this is the simple way that we can represent the operational amplifier circuit. And we discussed about the ideal operational amplifier. Under ideal condition, we assume several things. There are several assumptions. One is infinite input impedance, because I told that input resistance is large, but under ideal case, we assume this is very large or that is infinity value. And also we assume infinite gain for the differential input signal. What is differential input signal? Difference, that is between V here, because if we give two voltages, we have here the V plus minus V, that is V plus minus V minus, right? V plus minus V minus. That is what we call differentially. That is difference between input voltages. And that also we assume that is gain of the differential input signal is infinite. That is A value, that is what we discussed here, gain A, that is V out over VD, V out over VD, that also we assume as infinite. And in addition to that, we assume output impedance as 0 and infinite bandwidth. Do you know what is bandwidth? What we call as a bandwidth. Normally, you know, if we get a frequency range like this is the maximum, and there is some value. This is kind of thing we call bandwidth, right? That is from the peak, there is a small deviation. This range is somewhat similar, somewhat closer to the peak value. Therefore, this frequency range we call the operation bandwidth. That is, the ideal is this center frequency, but when we goes up to this range, there is a small variation of the peak value, right? Normally, this value up to this bandwidth range is 70.7%, because here 100%. And when it comes to here, it is 70.7%, or what we called minus 3 dB. I think we discussed that at last week as well, right? This is we call bandwidth. So infinite bandwidth is also assumed. That is, in the throughout the frequency range, we assume the value is peak, right? So these are the assumptions in the ideal operational amplifier. So, right. Therefore, because we assume here infinite gain, that is A as infinity, but what is the value of A? A is equal, if V goes there, A is equal to V out over VD. That is the gain. No? V out over VD supply. Then what we mean? A goes to infinity. A goes to infinity means this VD goes to 0. Right? So VD 0 means what we can see here, the difference between this voltage and this voltage is 0. That is same voltage. Here and here same voltage. Right? That is the positive side and the negative side. The difference is 0. Therefore, same voltage. And not only that, what happened if there is the same voltage? Here to here same voltage means what can you say about the current through this? Current should be 0. No? Because there is no voltage difference, then current is 0. Therefore, the current through this op-amp is also 0 in this condition. Right? There is no voltage difference. There is no current. Input current is 0. Right? So therefore, this situation we call summing point constraint. That is, the differential input voltage and the input current are forced to 0 under this ideal condition is called the summing point constraint. Normally, we analyze operational amplifiers assuming this summing point constraint. That is, we always assume there is no voltage difference between positive and negative terminals. And also we assume there is no current flowing through the circuit op-amp. Right? In the external circuit, there is current flow, but through the op-amp, there is no current flow. So these are the basics of operational amplifier. So based on this, right, there are various types of operational amplifiers. So let's see one by one. First, this is inverting amplifier. This is what we call inverting amplifier. What you can see here. Here, you can see the input signal Vin. Vin is connected to the inverting terminal through resistor R1. Right? Input signal is connected to inverting terminal through resistor R1. And output terminal, this is the output terminal. Output terminal is connected back to the input inverting terminal through a resistor R2. This is we call negative feedback. Negative feedback. Output terminal is connected back to the inverting terminal through a resistor R2. And how about the non-inverting side? Non-inverting side is right. What can you say about the non-inverting side? It is connected to the ground. It is connected to the ground. Then under the summing point constraint, what you can say? Here you know obviously this voltage is 0 because it is connected to ground. right? Here voltage is 0. Then how about this? Because under summing point constraint, we assume V minus and V plus as the same. Therefore, here also voltage 0. And how about the current through this? This current? That's also under summing point, we assume 0, no current through this op-amp. Then what happened to the circuit? There is an input signal, there is a current flow I1, let's say I1, that current is flowing through here. Right? Because no current flowing through that is inside to the operational amplifier. Therefore, current flowing is from starting here, goes through like that. This is the current flowing path. Then what can you say about I1 and I2? Should be same, right? I1 and I2 should be same. Because no current through this part, therefore what is I1 is flowing here and that is also flowing through R2. That is the properties or the what can we see in the inverting amplifier. Then let's see what is the amplification gain or the closed loop or that is the circuit gain of an inverting amplifier. So if we start from here, now you know positive side voltage, negative side voltage, both are 0. Then the I input is also 0. What can you say about I1? This I1, you can write as here voltage V in, here voltage 0. Then I1 you can write as V in minus 0 divided by R1. Therefore, I1 equals V in over R1. Right? And also I1 and I2 equal. Therefore, you can write I2 also equal to the same value. Now, what happens? If you write the voltages, here V output, right? V output plus I2 R2. That is again equal to voltage at this point. That is again 0. Because here 0, then therefore that point also voltage is 0. Therefore, V naught plus I2 R2 is equal to 0. Right? That is written here. And now, if you substitute I2 and solve, you will obtain V naught over V in. V naught over V in equal minus R2 over R1. We know gain is the output over input. V naught over V in. That is given by R2 over R1, but value is negative. That is why this is called an inverting amplifier, right? Inverting means the signal is inverted or out of phase. Output signal is out of phase. And its magnitude depend on these resistor values. That is, if we select R2 into a large value and R1 into a very small value, we can obtain a very large gain. Therefore, solely depend on the resistance values, the gain of this inverting amplifier. Right? So, and before going to the second type, I want to say how we analyze the operational amplifier. Just first what we do, as we already do in this example, first what we do, first verify the negative feedback. Here you can see that I told you the negative feedback means output terminal should be connected into the inverting terminal through a resistor. So in this figure, you can see that no output is connected to input through a resistor. Therefore, it has negative feedback. Then assume summing point constraint. That is, you assume voltage at positive side and negative terminal same, right? Not 0, same. But depending on the circuit, it can be 0. In this example, it becomes 0. If not, both are same. And the current flowing through this op-amp is 0. Assuming that summing point constraint, you have to apply different standard analysis techniques. That is, you can use Ohm's law, Kirchhoff's law, or any other circuit laws, because we discussed about various theories to analyze electric circuit. So using any of that method, you have to analyze this circuit, right? That's very simple. So therefore, now we followed that technique for the inverting amplifier, and we obtained that gain is equal to negative or minus R2 over R1. And next type. Okay, before that, see this example. This is op-amp, VI 0.5 volt. Calculate the output voltage V naught and the current in the 10 kilo ohm resistor. What is the type of this operational amplifier? This is similar to what we discussed here, right? The input is connected into the inverting terminal and the non-inverting terminal is grounded, and there is a negative feedback. Therefore, without analyzing, just referring to this, you can say gain is equal to minus R2 over R1, 25 over 10, that is 2.5, the gain of this amplifier. Or using simply the circuit analysis techniques, you can calculate. Here, voltage is 0, then voltage here also 0, here also 0, then current I, same current flowing through this, right? Then I you can write as VI is 0.5, 0.5 C minus 0 over 10. Again, you can write I as 0 minus V naught over 25. So then by solving, you can obtain what is V naught. So you will get V naught is equal to minus 2.5, 25 over 10. Not V naught, the gain, right? Gain is 2.5. Then V naught become minus 2.5 times input. Input is 0.5. Therefore, that become minus 1.25 volt output signal. Input is 0.5. And then the current I is equal to VI minus 0 over 10. By solving, you can get current is 50 microampere. I think that's okay, right? If you have any questions, please ask at any time. And the second type, non-inverting amplifier. What can you see here? Non-inverting amplifier. Here, the signal or the input signal is connected to the non-inverting terminal, right? And the inverting terminal, you can see it is, here also you can see the output is feedback into the inverting side through a resistor. No? Output is feedback to the inverting terminal through a resistor R2. Therefore, here also you can see the negative feedback. And signal is supplied into the non-inverting terminal. Now, what happened if you analyze this circuit? What can you say about here? This voltage V1, here 0. That means here also voltage is V1. No? This voltage V1. Then what is the voltage at here? V1 means this point also V1. Here also V1. Then this positive side also V1. No, because under the summing point constraint, this voltage and this voltage same. What can you say about this I1? Anybody? What happened to this I1? Can anybody say what is the value of this I1 under summing point constraint? Can I ask from somebody? Kusal. That's the first name I can see. What is this I1 value? Kusal, are you here? Maybe not presenting, right? Navod, or Navoda. Anybody tell me what is the value of this I1? Ilshan, Lochana. Okay, 0, 0. You are sending messages. Maybe any issue with your mic? Okay. Many of you are telling that is 0. Yes. Under summing point constraint, this is 0. Yes. Now you can analyze this circuit. I1 is equal to here V in minus V1 over, there is no resistance, right? Therefore, V in equal again V1. No? Because there is no any resistor. This voltage V in, this voltage V1, that also then equal. Okay, let's see here. Then the positive side, V plus, V minus, both should equal to V in. Right? And input current I1 equals 0. And V in, this V in, now voltage here. Again, it is equal to this V1 because from this side. Now, V in equals V1. So then by solving, you can write V in equal V1 equal. What is this V1? From the voltage division principle, you can write V naught. This is the total voltage. V naught divided by R1 over R2 into R1. From the voltage division principle, you can write V1 like this. Then by solving for the gain is the V naught over V in. So by here V naught and V in, you can get value is equal to 1 plus R2 over R1. Therefore, for a non-inverting amplifier, you can see gain is a positive value. It is value is equal to 1 plus R2 over R1. Therefore, that also depend on these resistor values. Gain depend on these resistance values. By choosing values as we want, we can obtain very large value for the closed loop gain. Right? So this kind of configuration we called non-inverting configuration. Now look at this example. Here you can see the non-inverting side or the positive side is connected with signal input, and into the inverting side there is a negative feedback. Therefore, you can assume summing point constraint and you can solve. This is very similar to this, right? So therefore, gain should be 1 plus R2 over R1. Or you can solve this. What is voltage here? What is this voltage? This point that is connected with 4 volts. Therefore, this voltage is equal to 4. Then how about voltage here? That also becomes 4. No? Current from here to here, 0. Assuming that now you can solve. Here then 4 volts. Here 6 volts. Then what is this current? 6 minus 4 over 4 kilo ohm. Again, you can write the same current. 4 minus V naught over 10 kilo ohm. Then you can calculate what is V naught because all other values you know. 6 minus 4 over 4. is equal to 4 minus V naught over 10. From that, you can calculate what is V naught. V naught should become minus 1 volt. Okay, very simple calculation. Op-amps are very simple, so you can easily solve. That is non-inverting. Next type, sum-in amplifier. Sum-in amplifier is the extension of the inverting amplifier. That also input signal is connected into the input terminal, but there are more than one input signals. Here you can see two, but it should be more than two as well. Several voltages we can connect it to the inverting side. And also there is a negative feedback. You can see output is connected to the inverting side through a resistor. Therefore, you can see negative feedback as well. Therefore, you can assume summing point constraint and you can solve this amplifier as well. Here also this voltage is 0, then this voltage is 0. There is no current, right? No current through this. Then I1 is equal to current through RA plus current through RB. Addition of that equal I1. That I1 is flowing through this RF. No? This I1 flowing through like this. Okay, try to solve this. Very simple, right? So V plus equal, V minus equal 0, I in equal 0. Then what is I1? Current through this branch, that is equal to VA minus 0, because here 0 voltage. Here also 0 voltage. Right? Because these all are connected. Then, sorry, VA over RA, current through this branch, VB over RB, addition is equal to I1. I1 equals that. Then from this part, you can write V naught plus RF I1 is equal to 0, voltage at this point. Right? Now, if you get here same RF I1 into the other side, and by substituting this I1, you can obtain this expression. V naught is equal to minus RF in brackets VA over RA plus VB over RB. And just for the simplification, if we assume RA equal RB, same resistances in both parallel branches, then V naught become minus RF over RA times VA plus VB. But you can see addition of voltages. Addition of voltages has been multiplied by feedback resistor over this resistance, if it is equal, right? If not, the expression is like this. That's okay. Sum-in amplifier. See this example. Calculate V naught and I naught in the op-amp circuit in figure. Here you can see it is connected to the non-inverting terminal. There are two parallel branches and that is non-inverting side is grounded. Therefore, this is similar to the earlier discussed question. We assume start from here. Voltage is 0, voltage is 0. Here also voltage is 0. And the current going through this part is 0. Assuming that, you can calculate. If you directly apply this equation, you can write this, but if it is, if you have to start, but that is if you have to calculate this as a fresh question, then you have to do the calculation, right? But because earlier we have done the derivation, here just have written the answer. V naught is equal to minus VRF over 5 into 2 plus RF over 2.5 into 1. And you will get output voltage here as minus 8 volts. And okay, again it asks to calculate this I naught. I naught is equal to, if we mark current as this direction and this direction in these two branches, I naught is equal to addition of here and here. Then what is the current through this side? Here V naught minus 0 over 2. Here V naught minus 0 over 10. That is equal to I naught. Right? V naught minus 0 over 10 plus V naught minus 0 over 2. These two currents. And you will end up with this value, minus 4.8 milliamp. That's fine. Right. Next type, differential amplifier. Differential amplifiers. Here the signal difference, that is what you can see in the inverting terminal, there is a input signal V2. And also in the non-inverting side also there is input signal. Therefore, under this operational amplifier, we can get the difference between V1 and V2 and some multiplication. Right? Let's see how it happens. So here, based on this configuration, what you can see, this is R1, this is R3, and this is feedback resistor R2. So, and if we assume voltage at this point as V, then also this point V, right? Because we don't know that value, you can assume V plus equal, V minus equal capital V. And input current into the amplifier is 0. Then what can you write? How can you write I2? I2 equal V1 minus capital V, V1 minus capital V over R3. Right? Also, this what happened to this I1? It flows through this branch, no? Because there is no current flowing through the amplifier. Therefore, this I2 flowing through this branch. If consider this branch, what is I2? V minus 0 over R4. That is V over R4. Similarly, you can write I1. I1 from this side, you can get V2 minus V over R1. Right? And again, it is equal to this current because no current flowing through op-amp. This I1 is flowing through here. I1 equal V minus V naught over R2. And again, if you consider here, what is this V? If you consider the voltage division principle, R3 plus R4, for R3 and R4, that is voltage drop is V1. Then for R4, it is V. Therefore, from the voltage division principle, you can write capital V is equal to R4 divided by R3 plus R4 into total voltage V1. right? Because this voltage is also, that is the voltage drop across both resistors is again equal to V1 because this is grounded. And V is the voltage drop across only R4. Therefore, from the voltage division principle, you can write V like this. Now, if you substitute this expression for V in this and this, you can obtain this expression. Right? Now, just by rearranging here V2 over R1, here minus R4 V1 over R1 times R3 plus R4 is equal to here R4 V1 over R2 times R3 plus R4 is equal to V0 over minus V0 over R2. That is only a rearrangement. Then by simplifying, you can get minus V2 over R1 plus V1 R4 over R3 plus R4. If you get into the outside, it equal 1 over R1 plus 1 over R2 is equal to V0 over R2. Like that, if you rearrange, you can obtain this expression. And if you get this simple assumption, right? R1 equal R3, R1 equal R3. These resistances are same. And R2 equal R4. These two are equal. Based on that assumption, only if that is valid, you can simplify this into this format. V0 is equal to RB over RA times V1 minus V2. That is the difference between the two input voltages multiplied by a resistor value. That is why we call this as differential amplifier, because this is the difference. Right? Although you see very large expressions, this is very simple, right? Just the rearrangement of the components. Next, integrator. This operational amplifier functions as an integrator. Here what you can see, non-inverting terminal is grounded to the inverting terminal. Input is given Vin, and also you can see there is a output feedback, negative feedback through this capacitor. Not through a resistor, but through this capacitor, there is a negative feedback. Therefore, you can assume summing point constraint in this configuration as well. Then what can you write? If you get this capacitor, this voltage, VCT, you can write as, because you know for a capacitor, you can write V equal 1 over C times integration of current. If we get current as I in, that is equal to I in times dt. Again, this I in equal from this circuit, V in over R, because here voltage 0, here also voltage 0 from the summing point constraint. Therefore, this V in minus 0 divided by R will give the I in. You can write like that. And also you can write I in because this current is flowing through the capacitor, right? Because the input current to amplifier is 0. Therefore, I in same. Therefore, assuming this branch, you can write I in as capacitance times dV over dt. Therefore, C, D, voltage difference is, here voltage is 0. This voltage is V0. No, because this side is connected to output terminal. Therefore, 0 minus V naught over dt. That's written here. Then by rearranging, you can obtain this expression. V naught equal minus 1 over RC integration V in times dt. That is, input voltage is integrated through the current time, and then by multiplying it from this 1 over RC value, you can get the output. That is how operational amplifier function as an integrator. These integrators has a lot of application, right? Because you know that you consider a signal from an accelerometer. You know, accelerometer, there is acceleration is given. No? So that is proportional to the acceleration. And if we integrate acceleration signal, you know, you can obtain velocity. That is the velocity signal. And again, if you integrate the velocity signal, you can obtain the position. So likewise, in mathematics, there are a lot of applications. Right. Next, differentiator. Similar to integrator, we can also get the differentiator if we consider this configuration. Non-inverting side is grounded, input terminal, there is a capacitor and resistor. This is the negative feedback resistor. Here what happened? V naught, because this current is equal to V in over, no, like this. If we get this capacitance, P times dV over dt is equal to minus V naught over R. Because you know the current through this, if you want to obtain current, here, how can you write? P times dV over dt. P times dV is V in minus 0 over dt, because here voltage is 0. That is written here. Again, you can write current as 0 minus V naught over R. That is minus V naught over R, because same current is flowing through here. This way. If you write I in this branch, you can write C dV in over dt. If you write for this branch, you can write 0 minus V naught over R. Same. Then by rearranging, you can obtain V naught equal minus RC times dV in over dt. That is, by differentiating the input signal, you can obtain the output signal through this operational amplifier. That is, the output voltage is proportional to the time derivative of the input signal. Right? Okay, those are the different types of the operational amplifiers. Any questions? Okay, let's move to the two examples, simple examples, and we finish. So consider this one. This is somewhat different configuration. You have to calculate closed loop voltage gain. That is, what is V naught over V in? Where can you start? Here, right? This voltage is 0. This voltage is again 0. Current this side 0. No current flowing through this. Therefore, what is the current path? Let's flow like this. Then at this point, it is divided. Again, at this point, it is divided. Current is flowing like that. This is simple, right? So what is the voltage? Voltage is V in, this voltage is 0. Therefore, you can write current through this branch V in minus 0 over R. Again, same current from here to here. Yeah. And let's say assume voltage at this point V1, then what can you write? 0 minus V1 over R. That is equal to V in minus over 0, V in minus 0 over R. From that expression, you can calculate V1. Next, you know, this current is divided between this branch and this branch. Therefore, current through this one, if we say I1, it is equal to I2 plus I3. Right? Like that, you can continue until the end. That. I1, I1 is equal V in over R. V in here 0 over R. I2 equal V in here I2 because I1 and I2 same. Therefore, I2 also equal V in over R. Again, you can write I2 as from this voltage it is 0, 0 minus V in V, let's say this is some voltage V1, then 0 minus V1 over R. Then by comparing that two, you can obtain what is voltage here. And if you solve, you will get that voltage as minus VE. Then what can you say about this I3? I3 is equal to then, if this voltage is minus V in, then I3 equals 0 minus V in over R, that is V in over R. Right? Like that, then you can write this I4 equal I3 plus I2. Likewise, you can continue this. And finally, you will get what is the voltage gain. That is, finally, you have to obtain what is V naught over V in. Right? This one, this is it. Right? If you continue that, I4 become this I4. 2 times V in over R, then the voltage at this node, you will get like minus 3V in. And next I5 and then I6 become 5V in over R. And the V naught node that is here, V naught node at this point. Voltage you will obtain as minus 8 times V in. Then you know that is the V output. Therefore, V output over V in is equal to minus 8 V in over V in minus 8. Therefore, the amplification gain or the closed loop gain of this operational amplifier is minus 8. That is, it is the inverting amplifier. Okay. How about this one? Try this one. Just very simple tricks are required to solve this. What you ask to calculate, what is I naught? What can you say about this? How can you calculate I naught? What is the current flow in path of I naught? Because you know there is no current, right? Here, therefore, here also no current. Zero. And this section also current is zero. This also current is zero. Then what is this I naught path? It is flowing through here, come through this end, then right end here. That is the I naught path. Then you can calculate I naught if you know voltage at this point and this point, right? If this is V1 and this is V2, then V1 minus V2 over R. What is the voltage at this point? Here it is V1, no? Because this side is connected to V1. Then this voltage also V1, that means here also it is V1. How about here? This is connected to V2, therefore positive side is V2, then negative side is also V2, therefore then this point also V2. Now you can easily get I naught. V1 minus V2 over R. This V1, this V2 over this R. Okay. Right, that's only under the operational amplifiers and all the theory parts what I have to discuss.
Recording stopped.
Any questions from today's lecture? Okay, so then you have tutor class at next Monday for both EE and CSE students at the normal lecture time, that is from 10:15 to 12:15. I will do tutor class online, right? Use the same Zoom link what you logged today. So make sure to join the session. That is tube 2, and then we have to discuss tube 3, that is from this resonance part. And after that, I will give you in-class test. Okay, so for that also we have to decide the date. Anyway, I will try to finish all the tubes before the April holiday. And then after the New Year holiday, you will have the in-class test. That is my plan. And therefore, from next Monday, I will take the tutor class. And after that, 17th Monday, I think that is a holiday or a semester break. And from 24th, Professor Vikramaranchi will commence his lectures. Okay. Right. So then thank you for joining because it's at the night and participants are very less anyhow. So I will upload the recordings as well if you have missed some part for both the sections last week and this week. I will upload the recordings to the Moodle. Okay then. Good night to all of you and thank you.